Okay, so we will first continue with a talk about real-time packet inspection from Dr. Razvan Bocu. But also there is another talk in the other room, so that was scheduled just now. But please enjoy the talk by Dr. Razvan Bocu. Okay, you can start.
Okay. Thank you for the confirmation. And just to check with you, should I share my presentation, I suppose, isn't it?
Yes, if you have one. Otherwise, we
Yes.
also enjoyed just seeing you.
Sure. I'll share my screen. Okay, so can you see my presentation?
Yes.
Okay, perfect. So thank you for the initial introduction. I am just to say a few words about me. I am a research and teaching staff member in the Department of Mathematics and Computer Science that is part of Transylvania University of Brașov in Romania. And the talk that you are about to watch concerns the description of a contribution which values the experience that we gathered during the implementation of some 5G services here in Romania. So the agenda is composed of the following sections. First of all, I'll briefly discuss about the relevant technical requirements. Then I'll go through the relevant technologies. Furthermore, the intrusion detection system will be presented, followed by a description of its performance. And finally, the last part of the presentation concludes the talk. So we have envisioned the following concepts throughout the reported research. First of all, we dealt with high throughput data channels. We have observed that when we speak about smart applications of various kinds, usually in order to ensure a quality end user experience, we should be dealing with at least 25 megabits per second as channel bandwidth, and these are intended to support the well-known applications such as virtual reality or augmented reality. We have had the requirement to ensure that the designed network is scalable and structurally flexible. And this, especially this latter requirement was affected by the consideration of network functions virtualization. Then we have spoken about very low latency for the 5G Internet of Things data channels. Then reliability and resilience, data privacy and security. We have processed highly sensitive data such as personal medical data. And this is a natural requirement. And not the least important, we have envisioned the long battery time. Furthermore, there are some other requirements such as connection density and mobility. Okay, so I'll briefly talk about virtualize the wireless network function. It's the fundamental process that was considered during the implementation of the infrastructure that I report in this research. It has been effectively used in order to deploy the core of the respective 5G networks. The reason is fairly straightforward to explain, as it ensured that a self-sufficient 5G network was created, and it was easily deployed and maintained on the respective hardware infrastructures. It is relevant to say that we have effectively used this mechanism for the implementation of quite specialized network services on the 5G network. And right from this state of the presentation, I can say that we have observed that the virtualized network environment provides logical flexibility and scalability, and these were one of the most important initial requirements. And they allowed us to efficiently deploy the real-time intrusion detection system that I am speaking about. The intrusion detection system considers an architecture that is respecting a three-layered structure. First of all, the data packets are connected through the initial forwarding layer, which implement a kind of object file system. They are forwarded to the management and control layer, which perform some pre-detection and pre-calibration tasks. Then it's forwarded to the data intelligence layer, which performs the actual detection of the possible malware patterns through some machine learning algorithms that are implemented. Okay, so as I said, the forwarding layer is responsible for the data traffic packets monitoring and capturing, while the data management and control layer identifies the suspicious data patterns and detects anomalies using the intercepted data. If necessary, it takes adequate protection measures according to the decisions that are made by the data analysis layer. Okay. In this context, it is useful to discuss about the packet collection and data flow partitioning layer, which is the component responsible for the provision of a more global view of the entire 5G network. Furthermore, it's relevant to note that the status monitoring module supervises the data network status and continuously analyzes the data packets that are received in order to ensure that a proactive and almost real-time analysis is being performed. Additionally, it contributes to the creation of relevant clusters of data packets and also generates a data fingerprint that keeps track of the following logical network parameters. They are the source IP address, the destination IP address of the respective packet, the source port, the destination port, session duration, and finally, the considered network protocol. These data fingerprints are used in order to basically label various data flow records that designate and represent specific network connections and activities. The packet collection and inspection is performed in a continuous fashion, and this practically continuous fashion is determined by a data collection and inspection interval that is optimized in order to avoid possible delays that are not desired, certainly. And the anomaly detection considers some basic flow statistics that are useful in order to detect abnormal behaviors and potential anomalies. Just as a side note, these have also the role to ensure that the false positives rate is kept at the minimum possible level. Speaking a little bit about the algorithmic machine learning based core, this system considers an entropy based analysis, which is based on the well-known Shannon's theory, that in this context is able to detect the distribution variations of the analyzed data packet samples. Speaking about the entropy that I have just mentioned, this is determined by a function whose formula is represented in this image. And the components of this formula are the following. So P of x index I represents the probability for x to take value x index I, considering all the already detected values for the already intercepted data packets. As I have already stated, 4 fundamental parameters are considered. These are the source IP address, the source port, destination IP address, and destination port. And these are acquired by the real-time traffic analysis component. Speaking about a certain particular moment in time, the continuously updated value that this entropy function provides significantly supports the accurate detection of malicious data traffic patterns. Furthermore, speaking about the math and the algorithmic that stands behind the detection process, considering that E stands for the mean entropy and S represents the corresponding standard deviation, a possible suspects pattern involves that the value of the entropy function h of x is outside the interval that you see here, e minus s, e plus s. So if this condition is met for some potentially suspect data packets, they are sent over to the proactive data analysis layer for supplementary analysis. Speaking about a machine-based data analysis, machine learning-based data analysis component, it is fairly natural to say that the feature selection component is important and is engineered in order to build and update the feature set that is determined by the detected data patterns. We have experimentally observed that the component is capable to process fairly large amounts of data in a near real-time fashion. And it is also capable to remove the data features that are not relevant to the machine learning based detection core. And consequently, the data is partitioned into the relevant categories. What I'm explaining here follows a fairly standard design of a machine learning based system. I won't insist on the details of the algorithmics of this machine learning based system, but if some of you are not proficient in this respect, the information is certainly easy to find in the existing literature. And of course, I would be more than happy to clarify it. I'll go further and I'll say that this selection component is capable to remove, as I said, the data patterns that are not relevant. And what I would also speak about, it's some technical details concerning the performance assessment process. So the analysis, the performance analysis process, which supported the iterative development of this system, considers data that was effectively gathered during the real-time intrusion detection deployment. And the data set considered 32 million analyzed network connections. Each individual connection pertains to 39 features that are separated into 3 categories. Thus, these categories network connection based features, content based features, and data traffic based features. Additionally, it is I would say important to know that each data traffic entity is marked either as a normal traffic entity or as a suspicious one. The ones that are deemed as potentially suspicious are also grouped into 4 distinct categories. These are remote to local, probe, user to root, and lastly, denial of service. We have considered several metrics in order to assess the performance. These are precision, reliability, trade-off, accuracy, and the false positives rate. In short, the precision is defined as the percentage of valid malicious data traffic predictions relative to the total number of predictions that are made. Furthermore, reliability is computed as the total number of properly determined intrusion attempts in connection to the total number of intrusions. The trade-off designates a hybrid performance metric that considers both precision and reliability. And its role is to offer a better accuracy of the data classification through this formula. In this formula, P comes from precision and R represents reliability. Moreover, the accuracy is a ratio that is computed as the sum of the number of legitimate packets and malicious packets properly detected at the numerator, while the denominator of the ratio is the sum of the accurately detected legitimate and malicious packets plus the incorrectly detected legitimate and malicious packets. While the false positive rates, it's pretty forward to understand, so I will not insist on it. We have created chunks considering the overall data set that we had at our disposal for the performance testing. Basically, we had 5 main chunks of data that consider between 20% and 100% of the overall testing data. And we have assessed the values of the already mentioned metrics. And the values can be seen in this table. You can see that the values of the main metrics, mainly the performance, for example, and the reliability is kept at a sufficiently high level, regardless of the size of the data chunk, while the false positives rate is fairly at a fairly low level. Moreover, it is useful to say that according to the experiments that we made, the value of the false positives rate was so low that the system was capable to properly perform the detections of the truly malicious data packets, even when it was fed with large amounts of traffic. And as some conclusions that were extracted after the design, implementation, and after the performance assessment process, we can mention that the system scales well, as we have already said, and it is also capable to properly detect the malicious traffic patterns while reducing at the minimum the incidence of the false positives. If the rate of the false positives is higher, then the system may get overloaded with data traffic packets or patterns that are not actually malicious, and it may become less responsive than we would like. And this real world behavior of the system is especially important in the case of commercial 5G data networks, which by their nature transport and provided after the performance assessment process. I can say that the system is capable to ensure that the detection does not impact the overall function of the 5G data network. And while it is detecting the traffic patterns with the values of the performance metrics that were mentioned, the overall function of the data network goes on smoothly without any adverse effects to the end users. Okay. And I have consolidated the findings that are reported into a paper, which may be published after the conference in the proceedings. And in that proceedings, some further considerations are being made in connection to the problematic that is presented by the paper. I am perfectly aware that the topic presented cannot be fully covered during a single time slot at the conference. So I am fully open to any further questions even after the conference. And you have here my contact details. And also, I'm open to any potential collaboration that you may be interested to propose. Furthermore, I hope that next year we will be able to meet in person at this nice conference. Thank you for your attention, and if you have questions, you're more than welcome.
Thank you. So, are there questions from the audience? No. So, a question from my side. You mentioned like the 25 megabits of traffic. Did you go any higher? So, like to have like the full bandwidth that 5G networks are capable of, and analyze them?
Yes. During the experiments that we made, we have deemed that this 25 megabits was the minimum necessary bandwidth that would ensure a proper level of the service, of the quality of service. And during our experiments, we have gone all the way up to 1 gigabit. That was not part of the commercial section of the network. So the section of the network that was currently offered to the customers. It was a section of the network that was provided by us experimentally. But yes, we have considered up to one gigabit of bandwidth. Yeah.
Okay, sorry, there's one more question. Sorry.
Regarding your false positive rate, you had about 1%, and you told us it would be fairly low. When I have a 5G network nationwide or even a regional, when I think about 1 million packets I have to inspect, and I have an error rate that gives me false positive alarms at a rate of 1%, that would be a fairly high amount of false positives. Some human operator or another checking system has to approve or disapprove. What's your opinion on this point of view?
Your opinion is absolutely legitimate, and it is valid if we speak about an approach that considers mostly, let's call it manual assessment of the of this packet status. But the system that we implemented and deployed is mostly an automatic one. So the packets that are falsely detected as malicious at the second level of the architecture that I described are sent over to the third level, and there the machine learning based components will realize that we don't speak about a truly malicious pattern, and they will be disregarded as such. So the problem that I could see is when significantly more packets are classified as malicious when they are actually not, as the third layer would become overloaded with unnecessary processing. And according to our experiments, I can say that an unreasonably high level of these false positives rate would be somewhere over 10% in the case of this system, but we have never got up to this point. And the value of the false positives rate that I presented in this table can be even further reduced if the routines that process the data packets are further improved and optimized. So it's an ongoing work. It's not perfect. It's ongoing.
Okay, thank you. Then I have a follow-up question. Then this was a misunderstanding on my side that the data, the metrics you presented were related to the second stage. Do you have any metrics on the third stage? And that's it also has a false positive rate normally. You could present. I would really be interested in.
I haven't prepared the metric specifically for the third stage, but I can prepare one if you want, and I can provide it to you, sure. But at the moment, I haven't prepared with the table specifically for the third stage, unfortunately. But we can keep in touch, and I promise that I will provide you the metrics that you require.
Thank you. Then I will email you.
Sure, I'm looking forward.
Okay, So I think we have no more questions from the audience. I didn't see questions in the stream. So thank you very much.
Thank you as well, and let us see next year in person, hopefully.
So this concludes the sessions for today. I hope you had a nice day and get some rest in the night. Don't party too hard because we're under COVID restrictions anyway. See you again tomorrow. Thanks. Bye.